Okay, physics problem 14, the swing. This one is a little bit challenging, and I think that these three parts will be part of the bonus. To tell you the truth, the physics kappa will be another scaled thing where to get 100%, you don't have to get the entirety of all the problems done, all the parts done. But these three, well, the first ones you'll see is not not tough at all, but the other two involve a little bit of work. So we'll see if I can get it all in one session here or not. Okay, and in part one, and you can see the answers there, and immediately everyone's pausing the video. I'm going to try zero. I'm going to try zero. Well, let me explain. So the swing, and he starts when the rope is perfectly horizontal. Okay. And if you have this here, and start gravity, yes, Fg is pulling down. But there's nothing tugging this line here to put tension in it, because gravity is straight down, is perpendicular to this rope. So now the millisecond that this goes down, it's no longer perfectly horizontal, so there's a little bit of a force that will be pulling on it. But the force, the tension in this rope is zero right now. So that's an easy first one right there. Okay? All right, now the scenario changes. In part two, okay, let me erase, well, maybe I'll erase this. We have the swing. Yes, I am going to erase it. Let's erase this. So this is part two now. Okay, the swing is 1.59 meters above the bottom of the circular arc. Now, these two are the same length, but they don't look it just because I'm trying to give myself some room. So from the bottom of the arc, it is 1.59 meters. This whole length is 3.04 meters. Therefore, this height that the swing fell is the difference in the two. So 3.04 minus 1.59, and we get 1.45 meters. Okay. What I'm going to do is use energy right now and to help myself out. And the goal is to find the force in the rope. But this is why it's a little tricky. You don't have to use this. You could actually use kinematics too, but I'm going to use energy. So we're not worried about part three. We're in part two right now. So what if this thing fell this far? How much energy was that? Well, that's PE mgh. So it is mass 72.2. Please use your own numbers, because if you use mine, that will cause problems. Gravity 9.81, and our height of 1.45. Okay, that gets us 1,027 and 0.009 joules. So let's find the velocity now. Okay, well, if all that energy was turned to velocity, what would be my velocity? KE. And so this goes into KE. So 1227, energy is conserved, 1/2 mv squared, which this is equal to 1/2 72.2 times v squared. So we're going to take this, divide by the 1/2, divide by the 72.2, take the square root, and we end up with a velocity of 5.333 meters per second. Now, we're finding this, first off, we're finding this centripetal force here. So this centripetal force is pulling this way, and so it's going to cause the tension, that's an arrow, happy little arrow, it's going to cause the tension in this way to get bigger. So we got to find this FC. Okay, that's our first goal here. Well, Fc is equal to mass times the centripetal acceleration. Well, how do we find that? Well, that is found with v squared over r. Previous formula we've used in previous problems. And this is 5.333 squared over our length of our radius here, 3.04. And that gets us 9.355 meters over second squared. It's an acceleration. Okay, now we can fill in to find this Fc. Its mass, 72.2 times 9.355, which equals 675.47 newtons. You're like, hey, yeah, I'll put that in the answer. Oh, wait, it's different. That was our answer. Yeah, we got a little bit, we got one other force to figure out. So yes, you found this, and that does cause this. But what also is causing a force? Well, gravity. We haven't added gravity into this tension. So we got to do that part there. So let's just containerize this. We will need this answer in the last step. So let me do some purple here. We will need this. So please do not lose this number. Okay, so we're going to split gravity. So let me go over here. So gravity is pulling straight down. But we need to change it by making a right triangle. And this is the hypotenuse, though. This has to be the hypotenuse. So what we're going to do is we're going to make a triangle like this. So I'm going to redraw this. We're splitting gravity. So gravity is straight down. And we're splitting this piece into this and this piece. And this piece will be, if you notice, this piece will be in the same line with this. So we can, remember vectors, you have to have them in the same direction in order to be able to add them and combine them. Okay, that's why we'd use sine and cosine to split these things to try to get them into the same, in the same line. So we need this angle in here. Oh, so we need this angle. It would be nice to know that. Ooh, well, we better find this angle because it will be equal to this angle in here. So we need to do a little trig for that. And so this is 3.04. This is right here. This is 3.04 too. So we need, we're going to do this triangle. So it looks like this. Sorry, here, and so we're going to make it like this. Sorry, there it is, there it is. This is getting a little confusing. So this is our triangle. So this is 3.04, and this is 1.45, and we needed this angle. So we're going to do the cosine of the angle equals adjacent 1.45 over opposite 3.04. Okay. Well, so you got to take the inverse cosine of this. When you take the inverse cosine of this, our angle equals 61.51 degrees. 61.51 degrees. So now, what we're going to do is, that's this angle right here, 61.51, and gravity, Fg, is mass times 9.81 for us, and so Fg is 72.2 times 9.81, and that equals, for us, 708 708.3 newtons. But now we got to split that. So this is 61.51 degrees. This is 708.3 newtons. And we need this F right here, so we got to split it. So cosine, this is your hypotenuse, there's your right angle. So the cosine 61.51 equals F of our G, we could add FGX if we wish, or FGY, and we could put the 708.3 under here. And when we solve, we get an FG of 337.83 newtons. Now, if we go back up here, we had our first force here, and that's in this direction right here, and we combine that with this, which is this force here. Okay, basically we have this swing, and we have, what do we have? We have this FGX, and we have this FC. So since the swing is not flying off, it is in an equilibrium position with this, the tension in here. These two have to equal this. So the equilibrium position in the x direction, if we set our axis this way, in this direction is 0. So the sum total of these two is 0. So these two have to add up to this one to cancel it out. They're opposite in direction. So what did we get? We have 337.83 newtons. That's this one. Plus this one. So this was 337.83. This one right here was 675.47 newtons. That's right here. Okay, I got that from right here, our previous calculation. And when you add those, you get 1,013.3 newtons. That's part 2. All right. Let's call that a day for part 1 and 2, and I'll get back with part 3 on another video.